Hey, welcome everybody. Thanks for joining me in my shop for Shop Talk. So, yeah, I think I got a pretty interesting topic tonight. We're going to talk a little bit about how heat transfers with different type of heat emitters and stuff like that. So I think it'll be pretty interesting. I didn't have a really clever demo to do with it, live demo, so I did like kind of a little a tooltip demo. I did some stuff over on my Vice here that we'll do a little video towards the end, and then see how that goes. But I got a nice plan for the next one. I'm on the back side of my display here. I've got some new stuff that I'm building. So tonight we're going to talk about transferring heat, and then I'm going to do hydraulic separation. That kind of ties in with the primary secondary we did last week. So it's, I think, kind of the next evolution on the way we pipe system. So that's a product that I know a lot about, working with Caleffi for the last whatever 12 years, whatever it's been now. So I've got some good information about how they work and why you might want to use one, and pros and cons. I'll tell you the good and bad news about them. Not every job needs a hydraulic separation, and so we'll dive into that a little bit. And I've got a good a demo. I don't know if you can see behind me. You can see the dog behind me, but I built a clear hydro separator, a 4-port hydraulic separator, so you can see exactly what goes on in there, how the flows kind of bypass, and it also does dirt and magnetic separation. So you can see all 4 of those functions when I run it on the display here behind me. So that's going to be a fun one. And then, yeah, last week's donation, we had a bunch of people tell us that they sent some some food down to the food banks, and we did also. So thanks everybody that supported us in that charity. And then we've got a choice for this week, and there's John Messenbrink, Mechanical Hub. Today, did you go by or something? John took some canned goods down to his local food pantry, so thanks for doing that. Yeah, we weren't quite 6 feet apart, but you were leaning out there a little bit, John, so that counts. And, oh, that's nice there. It's got one of the mechanical contractors on the truck too. Perfect. And so for this week's donation, we thought we would go with Meals on Wheels. You know, they do a lot of good out there, and there's certainly a lot of people. My mother's one of those. Mother-in-law is one of those. It's kind of closed in right now, not wanting to leave the door. So it's nice to have people like that that can deliver meals and keep an eye on some of the elderly folks out there. So thanks for supporting that for us. All right, so here we go. A lot of what I'll be talking about tonight comes out of issue number 23, hydronics issue that we did. We did an issue just, heat transfer and hydronic systems, and probably most of the slides that I'll be using come out of there. So hopefully everybody's getting these hydronics mailed to you. Twice a year we send these out for free. We'll mail them to your home or to your business, wherever you want them to arrive. And also they're available on our website as a PDF. And there's a lot of good information on there. We try and keep it as generic as possible. It's not always about Caleffi stuff. You'll see our competitors' product in there. It's just really a good, we like to call it a technical journal is really what it is. So, and if you want the back issues, let us know. We have some of those available still too. And one other thing I would ask, if there's a topic you think that we should be talking about that we haven't already, or that we should talk about again, maybe, let us know, because we're always looking for new things to talk about that can help the industry in general. It doesn't have to be about Caleffi products. In fact, the next one's going to be on air to water heat pumps, which is getting to be a pretty hot topic out there. So we're going to try and talk about that a little bit. And then, the heavy lifting goes to John Siegenthaler, does most of the work. I'd like to take credit for these, but a lot of my pictures show up in them, and Siggy will come up with an idea or concept and send it to me, and then I go back in the shop here and build it up and see how it works and try it out. So some of the homemade looking pictures in those are probably from my shop, but John does most of the calculations and the heavy lifting on those. So I don't know if he's on board today, but thanks for that, Siggy. All right, so hey, we're going to do this for our giveaway. We're going to have some of these Shop Talk t-shirts made, and we found a company that prints on demand, which is nice. For a couple reasons. Is number one, you don't have to buy a case of them to get all the different sizes, and there's a couple different selections of shirts and stuff on that, so we can get the get the size that you need and want. We can get them printed one at a time, or 10 or 20, whatever it takes. So I'm going to do the trivia, I guess, question right on the front end here. This one's going to be a little tougher on the lyrics from a song, and I want you got to know the name of the song and the artist on this one. So 2 things to win the t-shirt there. So the lyric goes like this. It goes, more bills than cash, I can do the math, trying to stay focused on the righteous path. That's the lyric, so I can repeat it if everybody didn't hear that. It didn't come through clear. So more bills than cash, I can do the math, trying to stay focused on the righteous path. And I've been in that boat for a long time. When I started out, more bills than cash. Probably we've all been there at one point. Excuse me. So over there on the left, this is what we're going to try and get through tonight in the time that we have. Like I say, we'll go, I don't know, maybe 45 minutes here, then we'll do the little demo, a video, then I'll come back for any questions and stuff. But I won't read through all those, but they're all different ways that we transfer heat, you know, first from the boiler into the fluid stream, and then from the fluid stream into the different types of emitters. So I'm going to go through, you know, the most common emitters that we see out there, radiant slabs and stuff like that. But what I want to do is I want to start out and just clear up a couple things I didn't have maybe the best answer for last week. So the couple slides here just answering some of the questions that came that were typed in as we were going last week, and it had to do with pumps and piping on pumps specifically, you know, what to do and what not to do. The question I think was how many inches or feet of straight pipe upstream of the pump. And so there's our suggestion, 12 pipe diameters upstream. So if it's 1 inch pipe, you know, a foot, 2 inch, 24 inches. And that just makes sure that the flow kind of straightens out before it gets into the inlet side of the circulator. And the other things that we always want to avoid with any circulators, we don't want to put a real flow restrictive device on the suction side of it. Certainly a Y strainer, which we know plug up after time, and now you're going to starve that circulator for flow. So if there's a Y strainer, ideally a dirt separator somewhere in the system, you know, put it maybe on the inlet side of the boiler so we protect the boiler and the circulator. But again, we'd want at least 12 inches of, you know, pipe between any of these devices if you got a check valve or anything like that. And the other thing I wanted to show down here on the check valve, I'd like to see that the same thing about 12 pipe diameters away. Now, I understand that a lot of circulators have check valves built right into them now, so it's not an ideal place to put a check valve, but again, maybe it's the lesser of two evils. If people weren't using check valves at all, it certainly is nice to have a check, you know, built right into the circulator, but ideally it would be a little distance away from it. And if you do buy a check valve that you're going to put on the discharge like that, you want to get a hydronic specific check valve, not a swing check valve. Get something that's got a spring-loaded check in it and also a conical shape to it, so it's got a nice flow passage to it, so it doesn't make noise and vibrate and clatter around in there. So we make a check valve like that. Other people do too. Watts, Combraco make hydronic specific check valves if you want to put one in the system. I like them a little bit better than flow checks. You know, the old weighted style flow check, it just seems like a lot of iron, a lot of technology to do a simple thing, which is a half a pound of weight that the circulator opens up or pops open when it starts. So, and then the last thing, and we'll talk about this when I do an expansion tank specific session, it's going to be on the point of no pressure change and expansion tank. So we'll get into that a little bit more, why the tank doesn't want to be on the discharge side of the circulator there. So that'll be a whole nother shop talk.
Now, Bob, I know that circulator best practices are of the key most importance, but we have some answers to your trivia question.
Oh, great.
Yeah, Steve Martino, could the answer be the righteous path? Drive-by truckers.
Yes, it is. I thought that was going to be a pretty obscure one for somebody that I thought they'd have to put their thinking cap on, unless he Googled it. But that's it, and he's the winner, and we'll get you get a prize to you.
Yep.
And
Ding,
somebody
ding, ding.
Go ahead, Mary.
Yeah, thank you. Thank you for all who submitted, and I think you may have stumped folks initially, but then they caught on. So very good. Thank you.
We were chatting a little bit before we started, and nobody in my team knew the lyrics there, and they said, well, where'd you come up with that? And, you know, I listen to Sirius when I haven't been on the road much lately, but when I'm driving, and I just kind of switch between all these different genres and hear these songs that I've never heard before, which is kind of interesting and helps the drive time go by. And I just heard that. I thought it was a clever song. All the lyrics are clever in it, but yeah, so download that. Drive by Truckers, Righteous Path is the name of the song. Now, the other thing that we talked about a little bit last week, and it's going to apply to what we're talking about tonight, is how flow goes through a pipe or through a tube. And there's a couple different conditions that the flow can be in as it goes through a tubing, and it can be either a laminar or turbulent flow. So laminar flow, if you looked at it, if you could explode the view there, it would look something like this, where the water goes through kind of in just little cones like that. And it doesn't transfer heat very well because you get, well, you can read right up here, you get this little boundary layer along the outside wall of the tubing. So the heat that's within that water, glycol, whatever the fluid might be that's going through there, isn't in good contact with the surface of the pipe or your radiator, your heat emitter, whatever it might be. So if we're trying to move heat energy out of a fluid stream into a heat emitter, into a pipe, into a radiant slab, whatever it might be, we'd like to have this condition here where all that temperature is contacting the edges of the or contacting the wall of the pipe or the the wall of the panel radiator, cast iron radiator, whatever it might be. So we can predict when this happens in a tube if we know the size of the tube and we know a couple of pieces of information, and I'll show you how we do that. But one of the questions that came up, and I'll go back a slide here, when using the old style air purgers, the scoop or the ramp type air purgers, I heard somebody say, well, you want that 18 or 24 inches upstream of that so the flow can go laminar. Well, that's not exactly what happens there. The only way the flow can go laminar if you slow it way down, way down, below a foot per second velocity. So really with that straight section in front of here, I've got a cutaway of a scoop type purger. That straight section upstream of this is really intended to have the bubbles rise up to the top of the fluid stream before it even gets into the air purger, so it's got a better chance of getting out. We're not turning the flow into laminar condition as it comes into that. We're just getting the bubbles up to the top so we can evacuate them out of the purger a little bit easier, a little bit quicker. So now I got a mess on my computer. All right, so one way that we know and predict the what the flow condition is going to be through a tubing is this thing called a Reynolds number. And so it's really a dimensionless value that just tells the condition inside a pipe. And so what they say is anything below 2,000 would be laminar flow. Anything that's got a Reynolds number above 4,000 would be turbulent. Now notice there's a little gap in here, and that gap is what they call the critical zone, and that's where the flow it's in transition, and it's hard to predict if it's laminar or it's turbulent. So there's a little bit of space, and I'll show you on a calculator next of where that falls. When you put a pipe size in, you put a flow rate in it, it's going to predict what condition you're under. Now there's the math for it if you wanted to do the math and figure that out. If you knew some of the dimensions and some of the fluid and stuff in it, you could calculate it longhand like that. But there's calculators online that you just plug in a couple of pieces of information and it spits that number out for you. Because again, everything that we do in hydronics, we want to be under this condition if we're trying to transfer heat. Now there is one condition where we might not want to go to turbulent flow conditions. And think about this: if you have take a district system, for example, we've got a central boiler plant, and maybe the pipe is going underground to all these different buildings. Well, we don't want to lose a lot of heat through that underground insulated piping. So an engineer might design that so it's working under laminar flow, a real slow flow condition under probably a foot per second velocity, depending on the pipe size, so that he gets most of the heat from the, from the heat generator from the boiler room out to the buildings before it gets lost to the ground. So there are conditions where an engineer might look at laminar flow and decide his pipe sizing and his pumping flow rates to stay under that condition. But once it gets to the building, once it gets to the heat emitters, we need to have this turbulent condition so we can exchange that heat out of the fluid stream as best we can. And by the way, it's happening as we speak in our bodies. As I was searching for, Reynolds numbers and turbulent flow, this came up. Who knew? I didn't know. But the same thing would happen, in our body. We want this type of flow condition. And if your veins or your vessels start to plaque up, or you start to get, a little bit of scale build up inside your veins, this is what happens. You get that little choke down section, just like when we have a balancing valve where we choke the flow down. And now we're going to have a little turbulent condition on the other side of that. And probably want to go to the doctor if they think that's happening. And what they'll do is they'll put a stethoscope, and they'll go around and they can detect that going on just by hearing that that condition that you get when you get turbulent flow, or when you restrict water or blood in this case through a restriction like that. And that's, you can see how the flow changes from turbulent to from laminar to turbulent conditions because of that restriction and that downstream turbulent condition. All right, so this, I think I showed this on one of the other ones, and I kind of like this. The Plastic Pipe Institute has this free calculator on their website. You have to agree to some terms to use it, but basically, this one's just for plastic pipe, of course, because that's the business they're in. But you just put the type of tubing in here. They've got PVC, they've got a bunch of different plastic tubes, and the wall thickness of the tube down here, PEX is the SDR, standard dimensional ratio of 9, the size of the tube, and then you can put in a flow rate, and it's gonna predict one of these boxes over here. So in this case, I just kept going down with my flow rate, going down until I could get the flow in that 3/4 PEX down to a laminar condition. And over here is kind of what I did. So to get down to laminar flow condition, I had to get down to 0.4 tenths, under a half a gallon a minute flow rate, to get down to a laminar flow condition in a 3/4 PEX. And at that flow rate, we're looking at a 0.4 0.4 feet per second. Think of water going through a pipe, how many feet per second, a half a foot per second, barely going to see that moving at that kind of flow rate. So then I just kept playing with this formula and just putting different GPN numbers to see where it went into transitional flow. So there you can see a point where I went into transitional flow, and then I wanted to see where I got up into turbulent conditions. So somewhere about 0.5, just over half a gallon per minute, I got up into this condition here, which would be good for transferring heat, out of that pipe into whatever it might be, a slab, or into a heat emitter of some sort. So most of the other piping materials out there, whether it's copper pipe, you can find a chart like this online. You can find one for steel pipe, Schedule 40, Schedule 80. One of the best resources I found for looking at other pipes is it's called the Engineering Toolbox. It's just a website that has all sorts of different calculators, and if you put in a flow velocity calculator, will come up, and you can input the type of pipe you have, the flow rate, the size of the pipe, the type of fluid, the temperature. I mean, you can really nail it down to a tight number. So this is we have those charts that are just kind of rules of thumb, saying the maximum amount of flow that you could put in an 1.25 inch pipe, copper pipe, whatever it might be. But this would be something you want to use if you really want to get that number exact, where you don't have to guess and say, well, do I have to go from 1.25 inches to 1.5 inches? What would happen to my flow velocity if I went 13 gallons a minute through 1.25 inches instead of the recommended 10 gallons per minute? So this is, all these tools are out there. They're available for free for the most part. So, take advantage of them. So here's what we know. The second law of thermodynamics basically simply says, heat energy transfers from a material at a given temperature to another material at a lower temperature. So hot goes to cold always. We can't make things cold. So if you put a 6-pack of warm beer in your refrigerator, what the refrigerator does, it pulls the heat out of that 6-pack and expels it to the outside of the refrigerator, either coil on the bottom or the coil on the back. If you put your hand on that, heat comes off of that. Well, that's the heat that it's pulling out of that warm 6-pack that you just put in the refrigerator. So heat goes to cold, and we know that with buildings, obviously, because the windows, the heat's going to try and go through all the low R values to the outside. And the rate of that heat transfer, how quickly that happens, or how quickly I can recover, say, an indirect tank, depends on the delta T, the temperature difference between them. So in this little example here, the hotter the temperature and the colder the temperature on the other side, the faster the transfer is going to be. So when we look at moving heat, we look at running at different delta T's. And if we can run at a wide delta T, we can move a lot of heat. And I'll give you some examples of type of systems that we run at wide delta T's or narrow delta T's. Why would you choose one or the other? What's the pros and cons of that? So same thing here. We look at heat. We can transfer heat 3 different ways, and we do in hydronic systems. We can do conduction, where if I put my hands around that coffee cup, I would feel the temperature coming out of the ceramic or whatever that cup is made out of. That's called conduction. Convection is what we do with a fin tube baseboard, where warm, cold air comes into the bottom, the pipe and the fins are warm, so it gets this little convection current going, warm air comes out the top. So you got cold going in, warm coming out. I could take a convection a step further and put a fan on it, then I've got forced convection. And then the last one, my favorite, is radiation. And when I'm talking about radiation, we're talking about light, basically. Radiant heat travels as a light. It's a light that we can't see. It's a spectrum that you can't see that moving, but that's how that energy transfers. And what's nice about that, it transfers in any direction. So I could have heat up on my ceiling. I could have a radiant ceiling. I would feel it down here. My walls could be radiant. As long as I have a visual, a line of sight to that, that heat will transfer from the warmer object to the colder object. And that's basically how the sun works. If you walk outside on a cold winter day and you're back in the shadow and you walk out into the sun and put your face towards the sun, immediately within seconds you'll feel that radiant energy from the sun. That's what, 93 million miles away, whatever it is. It travels through space that quickly, and as soon as it sees something that it can strike, you feel that heat energy being transferred. And that's how we do it with radiant surfaces, whether they're floors or walls or ceilings. So what we know also, that the heat output is fairly proportional to the difference between the supply water temperature, the temperature of the wall, the heat emitter, whatever it might be, and the room air temperature. It's a pretty linear thing, and that's why when we use an outdoor reset control on a boiler, the two follow themselves pretty closely. We step up or down the temperature going to the house as the temperature outside or inside, the building changes. So it's a pretty linear relationship to move heat based on the temperature difference. So and so that delta T, that the circuit's operating under is related to the ability of that heat emitter to give off heat. So if I have a wide delta T, I can move a lot of heat. If I have a narrow delta T, I'm moving a little bit less heat. So we'll show you some examples of that. And so when you go to design a system, you say, well, what's a delta T I should shoot for? What's my target? What's the number? And you know, we've used this number 20 for years. I don't know where it came from. It just makes the math easy. Maybe that was the simplest thing. But it basically, it doesn't have to be that, and the system doesn't have to stay at that 20-degree delta T. Of course, you know, from the turn on to the turn off point, it can vary a little bit, and it will vary based as the load in the building, as the load changes against that heat emitter, the delta T will always move. So if you put a bucket in front of your boiler and just put 2 temperature probes on that and just sat there for an hour, turned it on when a house is cold, watch the delta T, it might be 25, 30, even with a 20-degree design, until that fluid temperature starts warming up. There's a room where the load starts catching up, you'll see the delta P will close down until it gets to 0, which means the thermostat's turned off and there's no heat transfer obviously going on when it's 0 delta T. So these are typical numbers. Again, you could jump around anywhere within this range. For a radiant slab, we try and keep that delta T fairly tight, so the consistent temperature across the floor, if we walk from one end of the zone to the other end of the zone to the loop, it feels about the same temperature. So we want to keep usually a 10 to 15 degree delta T. Now that doesn't mean it won't go lower than that or it won't go wider than that. Fin tube, you know, 20 seems to be the number there. You know, we can keep it at that. It could be 25, it could be 15. Panel radiators, we can go a little bit wider, you know, 30 to 40 degree delta T is a fairly common design for a panel radiator because we've got a lot of surface area that we can work with there. And if you think about it, if we do a sim here, a snow and ice melt, we can move a lot of BTUs per square foot, 150, 200, even more, because why would that be? Why can we move so much more out of a square foot of concrete in a snow melt compared to inside the building? Well, the delta T. I mean, if you look outside and it's 30 degrees outside, the ambient air temperature on that slab is 30 degrees. If I'm supplying it with 100-degree water, I got a huge delta T to work with, so I can get a lot of BTU output out of a square foot of concrete if it's sitting outside where that wide delta T is driving that heat transfer. So, and these, I just got this picture today, thanks to Mark Etherton for turning me on to this picture of a really nicely made radiator. So really anything that you can get warmer than the ambient air temperature around it can be a radiator. It could be a wall, it could be a stair railing like this, it could be pretty much anything. In fact, I've done a couple of radiators over my lifetime just trying different materials to see what would happen. And this is in fact, I still have this. It's a concrete dog that I had one of those ornamental concrete companies cast this. And I took some corrugated stainless steel tubing to the guy and I said, you know, when you mold this up, it's a rubber mold that they put some rebar in. I said, can you put some tubing in there? So it goes up the rear leg of this dog and it winds around a rib cage in here, a rebar, and it comes down the other front leg here. And you can see the connections on the back there. So put 100-degree water into it and that's what you get right there. You get a cast concrete dog radiator. And we used to put our clothes and stuff on it just to keep it warm. So when you get out of the shower, you get up in the morning, you've got a clothes warmer, like a towel bar, but it's a dog. And we had a new puppy one time, he goes in there, starts barking at it, didn't realize it was made out of concrete. Looks like a foxhound. All right, so here's the heat output graph. So let's start, we'll put some numbers on this. I'm not gonna do a lot of math and a lot of formulas. I like doing the visuals, but it's important to know the math behind all these pictures and these visuals. So let's just, you know, design a system. Let's say we've got 100,000 BTU load, and we're gonna flow through this loop. Let's call it a fin tube loop. It could be a cast iron radiator. It doesn't matter what the heat emitter is. And we're gonna supply that with 180 degrees, and it's in a room with the air temperature, say 70 degrees. So a design condition, I designed this, so I've got about a 20, it came out to 22.9 degree delta T is at my design condition. So that's, you know, I'm just turning the thermostat on for the first time, the house is starting to come up to heat, I've got this kind of delta T. And so what's gonna happen is I start catching up with my heating load. Down here as my heating load starts being covered or catching up, you can see the delta T is going to close, and it's going to get smaller and smaller until it gets down to 0 when the heat load is covered. So this is a normal operating condition for a hydronic system where we're maintaining a constant flow rate. I'm not varying the flow rate through this, and I'm supplying it with a certain temperature, and that delta T is going to close up as the heat load goes away. And so think of that fin tube heat emitter, and so the air coming in starts out at say 60 degrees. I've got my design condition as it warms up and warms up. Now I've got less delta T between the air temperature and that temperature of the fin at say 170 degrees, whatever it might be, my delta T starts closing up. Eventually my thermostat satisfies and it shuts off. So it's really the thermostat that's in charge of what's going on in there. But this is what would happen if you just sat there and measured the delta T going out to that circuit and coming back. You would see that it would shrink as we get closer and closer to the load. Now, what we can do nowadays, which makes this even nicer, is we can put a boiler in there that can modulate with that load also, so we don't have to have a fixed temperature supply, and that's pretty nice. That's a good way to modulate the temperature to a load that changes. As you can see down here, as it gets warmer outside or whatever causes the load to change, warmer in the building, you're doing some cooking, whatever. It'd be nice to modulate that burner down and always match that load instead of shutting off, shutting on, shutting off, shutting on. And if we do that with temperature instead of flow rate, I can get a nice stable parallel curve, I guess you would call it, by modulating that temperature. And I'll show you in this example here. So when you design a fin tube system, this is a, John Sigenthaler sells this little simulator software here. It's really nice. It's got a bunch of different toolbars across the top. So I can do a heat load, a baseboard fin tube. I can do a circuit simulator. I can size expansion tanks. I can correct for different percentages of glycol, insulation factor on pipes, how that changes the heat loss, some fuel cost comparison. This one's really handy too. It's a buffer tank sizer. So I can pick a certain size of tank, put an operating condition on that tank, and it'll tell me what my run time, my boiler on and off time would be. So this is the baseboard simulator. And so what you do here is I can pick a pump. I think I put a Taco 7 in here. I put a supply temperature of 180 degrees going out to this, just a small fin tube circuit. I don't know, about a 20,000 BTU load. And so I can go in there and I can define, there's a pull down menu. I can put slant fin in there, embassy, whatever type of baseboard you want, different sizes of baseboard, different models of it. And then I put the load in up here. So if I had, I don't know, if I put in this great room, I think I might have had a 10,000 B2 load in there. It'll tell me the length of baseboard I need to cover that load in that room under this condition. What I like about this is every time you go to the next room, since I'm in a series here, it's going to tell me what the available temperature is at that next baseboard. So what I did on these bedrooms here is I put the same load on every bedroom. I call them the guest bedrooms or the kids' bedrooms. And you can see that the length of the fin tube starts to get longer and longer as I go around the circuit because my temperature is dropping. Even though I had the same BTU per hour load in every room, every time I go through a heat emitter, I drop some temperature. So instead of using the supply water temperature to size baseboard or using the average water temperature, if I said, well, if I start with 180 and I come back at 170, you know, my average temperature still hit emitters and size it by that, this is going to get it even a little bit more accurately because it's going to size every baseboard to the exact load in that room at the condition of or at the temperature that it's receiving as it goes through there. So there's an example where I can put a room name in there. I can put the type of fin tube I wanted to put in there, put my design load and put that in. And then once I accept that, this is what you end up with. So it shows me all the different lengths and all those different rooms as I go through the loop here. And I can play around with that. I could pick a different circulator pump. I could go a bigger pump. I could go a smaller pump. I could change my supply water temperature. If I wanted to put a percentage of glycol in here, I could see how that affects the heat output going through here. So it allows you to play all these what if scenarios before you even go and, you know, pick up the parts to build a job like that. I can say, well, no sense in putting, you know, the same amount of baseboard in every one of these rooms. You can see right here, my first room has 6 feet, had to go a little bit longer on the next room because I dropped that temperature from there to there. This baseboard is seeing a lower temperature. So it's just it's an accurate way to do a design, and it's, you know, you can play around with it. So let's say I've got, what, 6 fin tubes on that. Probably don't want to go much more than about 60, 65 feet on a series zone like that. I can just go down here and put another zone in them, and it would just split off another zone, and I could do maybe the upstairs or the basement as a separate zone. And the same thing, I could toggle on different circulators, different operating conditions, and just see what the result is, how much heat I'm going to move, what my temperature drop is through that circuit, all that stuff. So if you're doing this type of design work, this is a pretty handy little calculator to give all the information to you. All right, so now there's another condition that's going on out there in some of the pumping options that are available today. There's a delta T and a delta P pump. And what the delta T pump does, it tries to keep a set temperature going through the heat emitters all the time. So let's say you designed the system at a 20-degree delta T, the circulator is going to speed up or slow down trying to maintain that temperature all the way from start up to shut off. And basically, if you think about it, what it's doing, it's really kind of like an injection mixing where it's just pulsing that heat in there. You know, it's just trying to match the load by changing that speed of that pump. Here's one thing I want you to be aware of when you do that. So this line up here is what would happen if it was just allowed on a reset control to just operate at fixed speed on the circulator. This orange line, if you look what happens here, is the flow rate's changing on this orange line, and it's changing because the flow rate's trying to match that delta T that you programmed into that circulator pump. And so you're fine. I mean, that's good as long as you know that when you start getting down to these low supply temperatures where your boiler's ramping down on its outdoor reset and the circulator's still trying to maintain that 20-degree delta T, you can see that your output's going to drop off pretty quickly. In fact, when you get down to this point right here, you've got about 50% less output by modulating that speed, that flow rate down, as opposed to just letting the temperature go down in that loop. So just beware of that. Know that when you get down to the low end of that, you might get to a point where you're not going to cover the load anymore. You don't have enough flow going through that pipe to get the heat that you need to offset the load, let's say 4,000 BTU load there. So, and that's all knowable information. You know, you can put that in the previous slide I just showed you. If you had that simulator, you could put that in there and see what that condition would be if you kept that flow rate. So the other thing is when you try and regulate a heat output by varying the flow rate, it's a very non-linear thing. As you can see how these curves, or these two lines, these slopes, let's call them, they start to split apart. Where in the previous drawing, they paralleled each other. And that's why the outdoor reset can almost perfectly match the heat loss of a building, because it's the temperature is pretty closely related. You know, the amount of temperature you have to increase as the load on the building increases, and vice versa, is a fairly consistent parallel curve. So it makes it pretty predictable and pretty easy to dial in a boiler with an outdoor reset. You know, it might take a couple of trips back to get that number, but you should be able to modulate that boiler pretty much from a design day down to whatever the lowest turn down rate is and exactly match the loss of the load on that building. So I prefer to modulate the temperature as opposed to modulating the circulator speed. So especially if you're using outdoor reset control, because they're kind of trying to fight one another. The reset control is trying to tell the boiler one thing, and the circulator trying to do the opposite thing to maintain that delta T, so they kind of end up at odds with one another.
Hey, Bob, Steve had a question, if you don't mind.
Yeah,
he was wondering if that example was using copper fin or cast iron baseboard.
On the previous one, this was a fin tube that we modeled this with. Again, Siggy did the model, and there's 50 feet of 3/4 baseboard. And there's the output of the baseboard, and that's where we the math didn't come out exactly right, but that's where we tried to constrain, and that's what this is showing in this graph, is a piece of 3/4 fin tube. Yeah,
is it copper or cast iron?
Copper fin tube. Yeah,
okay.
I mean, if you use
that's copper. Okay.
Yeah, the baseboard, you could model that too, or the slab, which I'm getting to next. I'm going to do a panel radiator, a fin tube, and a radiant concrete slab. I didn't do a cast iron radiator.
And Ted asked if this also calculates the drop off in heat delivery as the flow becomes laminar.
Yeah, so that's exactly right. Somebody's following this exactly what I'm trying to show out. So you're going to get down to a point here. Remember I showed you earlier that on that 3/4, it was PEX tubing on that PPI calculator. I showed you when I got down to this flow rate, it was at 0.4. I think it was in that 3/4 PEX, which has a little smaller ID than 3/4 copper, of course, but I think it was at 0.4. And that's why this it would be in the toilet quickly here if you got down below that 0.4 GPM where you went to laminar flow. Now the water's just going straight through that tubing, and you're not getting very good transfer at all. So that's exactly what's going on there. So what we want to do now is we want to look at one of my favorite ways to heat a building. It was with a radiant slab. So we talked about how many BTUs per square foot is possible in a residential slab. So really the limitation on that is the surface temperature. You know, you don't want to get the surface temperature here too warm that people in bare feet would be uncomfortable walking on it. I tend to think, you know, in the mid 70s to high 70s is about right. You know, everybody's skin temperature can vary a little bit, but usually below 85 degrees, below 84 degrees is probably the sweet spot. Some people say down around 75 to 78. And so if you would look at that, if you're limited by that surface temperature, that's going to limit how much heat I can get out of a square foot of a concrete slab, for example. So let's use an 82 degrees surface temperature, and let's say the ambient temperature in that room or in that building is 68 degrees. 82 minus 68, the factor is 1.9 for a bare concrete slab without any finish on it. I'm going to get about 26 BTUs per square foot. So when you hear people say, well, the most I can get out of a concrete slab is 28 or 30 degrees BTUs per square foot, that's where that number's coming from. Now, if I was in a shop building where people in work booths or something all the time, I could raise that surface temperature up a little bit higher and get a little bit more output out of that slab. Again, if I'm at a residential application where I know people, might be walking around barefoot or something like that, they certainly don't want to have to put shoes on because the floor temperature is too hot. So that's really the driving factor on what kind of a, heat output you can get per square foot of a slab. Now, obviously, as you start putting floor coverings on that, you're putting R value on there, you're limiting that output. So, and here's let's take that number and just do a little snow melt here. And so let's say we're supplying 105 degree supply temperature to a slab that's in a 30 degree temperature, 30 degree ambient. Well, 105 minus 30 times 1.9, that's where we get such a massive output on a radiant slab that's outside as a snow melt instead of inside. I've got this big delta T that I'm leveraging from my supply water temperature to my ambient temperature. So that's how you say, well, how can a square foot of concrete give you so much different output? Well, that's the condition right there. I'm going to send you to my friend's website. I call him the Thermal King, Robert Bean. There's so much information on his website about all these different studies that have been done over the years about floor temperature and humidity. I mean, it really is a comfort site more than it is a heating site over there. And this is just one of the graphs that I got permission to use. And he's shown this design temperature here in this range. In fact, I think this article, one of these standards over here, ASHRAE standard 55, suggests 75 degrees being an optimum temperature. I tend to think, for me anyways, that's a little on the cool side. If I stepped on a 75 degree slab, while it might be covering the heat load, it might not feel warm to your customer's feet. So if they're expecting a warm slab all the time, that's probably getting a little bit low. So usually somewhere around that 82 degrees seems to be about right for me, surface temperature. And so that's going to dictate the output of this slab. Again, is the maximum temperature I can get on the surface of that. Now, know that I showed you on this one and that other FEA I showed you a little bit earlier, that's going to vary across the the surface area of the slab depending on the spacing of the tube. So if you've got 12-inch on center spacing, that high temperature is going to be right over the tube where it is, and it's going to get a little cooler between the tube until you get to the next one. So that's another little thing to do if you want a really nice consistent floor temperature, is get that spacing tighter, get it down to a 9-inch, even a 6-inch if you can do it, because that's going to even out that surface temperature, and it's going to allow you to run that slab at a lower supply water temperature to get that amount of output, because now I've got the whole entire slab at a consistent temperature instead of having that what we call striping, where you got warm over the tube, cool spaces in between it. In fact, of all the tubing that I've used over the years to do radiant slabs, the most comfortable one I found was, well, it was first called a solar roll, and then Heatway came out with that twin trend, and it was a tube right next to a tube. They're actually connected, and it was a counterflow. So you had hot going one way and the opposite on the other way, and it really, I mean, you could take your hand over the surface of that concrete and you could barely tell a temperature difference between tube and tube, because that counterflow design and that tighter spacing in that tube, it really evened out the surface temperature. So yeah, I mean, visit there if you have a chance. And Robert's always doing interesting things. He's got a new book out. He just did a study in collaboration with the BC Housing Institute, the education grants program back there. And so support his site and download this, and you can read it. It's a lot of information there. Some of it's, I'm punching a little bit above my weight on some of that stuff that he puts in there, but it's good information about other things you want to think about for comfort, not just the temperature of the room. Excuse me. All right. How am I doing for time? Yeah. All right. So here it is on a slab. And so what's interesting about this is, let's call this what we modeled here is a 300-foot loop of 1/2-inch PEX tubing in a 4-inch bare slab, a 12-inch on center. And what I'm going to do in all these instances here is I'm going to give them the exact same supply temperature. I'm going to keep that temperature consistent, and I'm going to change the flow rate. And look what that does to the delta T going across here. So on this one here, we're running this at a 25-degree delta T, so 110 coming out at 84. And you can see exactly by the color of that loop what happens. So if you get down to this part of the room or this end of the loop, that's not going to be a very comfortable floor surface temperature there, because I've run in such a wide temperature differential there. So all right, let's take and squeeze it down. Same temperature here. I'm going to squeeze it down to a 12-degree delta T, and you can see I'm starting to even that out a little bit better. I can go all the way down to a 7.3, and now you can see I've got a pretty consistent temperature from the front end to the back end of it. Now keep in mind, it's going to cost you more pumping power to do this, and that's going to be the trade-off, is how much circulator do I want to throw at this to get this job done. I'm of the opinion, as long as you're in a low to medium head circulator, that's not too much circulator. If you got to put two double 11 or 2699s, flange to flange together to get this to happen, that's probably not, a good design to do there. And so there it is right there. I mean, you can see as my flow rate changes, you can see how the output of that slab. Now notice on the red curve up there, you get to the point where a lot more pump gets you very little bit more output. So you can see I got a pretty steep curve going up, and then when I start to get out here, and this is kind of the difference between a 1 gallon a minute and a 4 gallon a minute on a fin tube baseboard, you get a little bit more output, but is it worth the extra pump to do that? You just got to run the numbers and know that, but you're going to get to a point where this is going to start to flatten out. Even if I went out here to 3-4 gallons per minute, not going to get that much more output, but it's going to start gobbling up a lot more pump horsepower to get you there. So what about low load radiant applications? So what we're finding in a lot of the new homes, especially the ones that are trying to get, green certified or LEED certified, they're getting pretty low BTU per square foot heat load numbers. In fact, we've seen some designs where single digit heat on a design day, single digit BTU per square foot requirement. So how do you get down there? Well, here's what you're going to run into. You're going to find that to put that kind of heat energy into a building in a design condition, you're going to have a pretty low water temperature to be able to do that. And again, right there, 73 degrees surface temperature to get that 10 BTU per square foot load. That's not going to be a warm floor. If you're selling this to a customer as a warm floor house, they're going to walk in there and say, my floors actually feel cool, not warm. And you're going to say, well, what's the temperature? Well, it's 72 degrees in here. Well, the heating system is covering the load, but it's not getting the floor warm to have to do that. So there's the math to calculate that. If we know what the load is on it, we know what the ambient air temperature, in this case, I'm calling it 68 degrees. To get that 10 BTUs per square foot, I only need a surface temperature of 73 degrees. Now, the good news about that, if I've got a ModCon boiler, I'm probably going to run that boiler at 80, 85 degree supply temperature. I'm going to have a great condensing condition and keep that up in the high 90% efficiencies. But, you want to make sure if the customer is expecting warm floors, that's not going to be the case. So this is actually John Siegenthaler's kitchen, and this he did back, I think, in 1979. He understood this heat flood concept, and that was a low load room there because he built a super insulated house. It looks like he's got a little air leakage around his doors. I don't know if it's Siggy's on the seminar tonight, but so what he did here, he said, well, what if I just loaded a band on the outer perimeter, don't put anything in the center of the room, and now my heat flux goes down, and it's going to drive the output of this up to, instead of 10 to 20, and now my supply temperatures to get that output are going to be at 83 degrees. So as you can see in the infrared picture right here, you can see in some spots, in fact, right on top of the tube, he's probably about 85 degrees. At 86 is the top end of the white. Down in here, he's probably in the mid 80 degree temperature across that. And the other thing you can see with the infrared scan is you can see that striping based on the spacing of the tube. So that's one way you could do it. I could still have radiant floor. I'm going to have a warm floor when I'm standing in front of these doors and windows here, and I'm going to cover my load even though I've got a low, low BTU per square foot requirement on it. So you could do something like this. You could maybe put some panel radiators in there also, would be another way to cover a low load condition. But just know that if I cover this entire room with radiant tube, it's probably going to be running at 70 degrees, and it's not going to feel like a warm radiant floor to the owner of that building. Same thing with panel radiators. So here's a really good look at a panel radiator under operating condition, and notice the delta T on this. I'm running a 40 degree delta T. I'm getting some great output on this because I've got a lot of surface area. I've got all that metal, and some of the panel radiators, I don't remember what brand this is, have fins in them, so I'm getting radiant heat off of this, the wave, the light infrared, but I'm also getting some convection current. So the cold air is going to come on the bottom. As you can see here, the darker colors, the colder temperature is going to come up, and you can see a little bit of convection current coming out of the top. So I've actually got kind of a dual emitter here that I'm going to, if I'm standing in front of it, I'm going to feel that warm metal radiating to me, and I'm also going to get a little convection kind of rolling the air through the room. just like you would with a fin tube. And you can see the difference here, the delta T shows up on the supply and return tube. And this, the nice thing about these panel radiators, a couple things is, number one, I can run them at a wide delta T, which means now if I'm returning this temperature, I'm in a great, again, condition for my mod con boiler. I can use really small diameter tube because I'm running that wide delta T, and I don't need a lot of pumping power. I don't need a lot of flow to be able to run that wide delta T. So my pipe size goes down, my pump size goes down, I get down into my condensing conditions with that low supply temperature. Not quite what I'm going to get with a radiant slab perhaps, but that's a pretty nice heat emitter. You can see why most of Europe is heated with panel radiators. I could put a TRV, a thermostatic radiator valve on that, and I could have room by room or even radiator by radiator adjustability on that system. Nice to have an infrared camera. You can really learn a lot just by looking at things, looking at the color and seeing what's going on, as opposed to always running the numbers and cranking the output on a graph or a chart. The color puts a little interest to it. So what about this? What about a system where I could run 92 degree delta? So look at this system here. I'm using a conventional cast iron boiler in this case. I'm going to run that at 180 degrees. And now out here on my radiant, I only need about 105 degree supply temperature. So all I need to do is take some small diameter PEX tubing, because I'm going to run this huge delta T here. I could probably feed that manifold with what, I don't know, maybe there's 10 loops on that with 1/2-inch PEX, because I'm leveraging this delta T. I'm taking 180 degrees out here. I'm mixing it with my return water coming back at say 88 degree, and that's how I'm getting that wide delta T. So now there's a system where I'm really leveraging wide delta T. I'm using small pipe, I'm using small pumps, because I'm leveraging that 180 to 88 degree delta T. Now that being said, I've got a boiler that's not going to condense, obviously, at those kind of operating conditions. So a little give and take here. To be able to run at that 180 degree, I probably wouldn't put a mod con boiler into that condition, other than, if I wanted the modulation aspect of it, I'd still have that, even though I'm running way out of where it's ever going to condense. And that's why in this example here, we've got a return protection valve on this, so to make sure that I'm always maintaining 130 degree return to that cast iron boiler, so I don't start sweating or condensing in that boiler. So just a basic three-way thermostatic valve will protect that boiler from running too cold. Yeah, I think I covered all that. All right, the last thing we'll talk about heat exchangers, then we'll do a little video. Yeah, there's different types of heat exchangers. This is what we call a tube and shell, coil and shell, flat plate heat exchangers. These are just ways that you can move heat from one fluid stream to another. I might use this for making domestic hot water. I might have a snow melt that I want to put glycol in. I want to run the boiler on regular water. I might use a heat exchanger like this. You can move a lot of energy through these little plate heat exchangers over here in these different type of heat exchangers. So sometimes you'll see a coil right in the side of a boiler, a tankless coil, just a cage of a copper tube that goes in the side of that. It's just basically a heat exchanger that's using the boiler fluid on one side, and the domestic water goes through the inside of that. And there's an example of a couple that I've got here in my shop. I actually cut one in half one day just to show a visual of how you can get so much heat transfer out of these tiny little heat bricks, we call them. It's all the surface area that you have in there. You can see all these passageways. Number one, you've got a lot of surface area, and you've got really turbulent conditions, because you can see as the water flows through those passageways, you got a lot of activity, and that's where you can get that good heat transfer, by having a lot of turbulent condition. If you put one of these in, there's a couple ways you can pipe them. You could go supply and return on both the A and B side, called a parallel flow. You're going to get a little bit better heat transfer if you do a counterflow, because again, you're using that delta T, the cold against the warm. You're getting a better exchange there, and that's just basically what these graphs are showing, the difference between the parallel and the counterflow and a flat plate heat exchanger. In fact, this is probably a better example of that. Now there's the math. If you wanted to run the numbers by hand, again, the best way to do this is just go on to one of the manufacturers of these, and most of them have free software simulation on their website that you can just plug in the flow rates, plug in the temperatures, and you can predict this here. But you can see not a huge difference between the parallel flow and the counterflow in this example here, but it just, again, depends on what you're asking or what condition you're putting that heat exchange under to determine that. And so what I would, if you want to, a little fuzzy unless I'm hallucinating, but that just a screen grab. So this is an example of the GEA website there. So all you need to know is all these different conditions. If you know the temperature on the A side and the B side, you can predict the amount of heat energy that this little plate heat exchanger can move. And you can play around with this. You can change the side of the temperatures on there. You can change the size of the heat exchanger. You can play different pressure drops with it if you want to make sure you can do it with a small circulator pump. Basically, you just change the dimension of the plates or the size of the external dimension of that, and you can really, you can nail these into an exact number. In fact, if you size one of these accurately and well enough, you can get what's called a close approach, where I could get pretty close to the same temperature coming out of this as I'm putting in the other side. So if you want to make domestic hot water, it's say you want 120 degree domestic hot water coming out of it, and you've got 125 or 130 degree on a solar array, let's say on the other side of it, I could get that heat exchange if I size the plates properly, get a big enough size that I could transfer that heat within that 3 to 5 degree close approach temperature range. So yeah, you can do a lot of things with those. And here's indirect tanks, just a heat exchanger if you think about it. So this is what's called a reverse indirect, where the boiler water would be in the tank, and then the coils, the copper coils, or sometimes stainless, is where the domestic water. So it's almost like an instantaneous tankless heater, in that the water gets heated as it goes through these loops inside there, and it comes out at the temperature. So and those can be nice buffer tanks also. You can use that as both your indirect heat source as well as your buffer tank for maybe a microzone system. And this is a nice way to do it, in that you can just buy a blank tank. You could just buy a inexpensive electric water heater, just a plain steel insulated tank, and then put the heat exchanger on the outside of it. Now it's going to cost you a circulator pump to do that, but the nice thing about that is you can size that to exactly what the load is. If it's doing a domestic water load, or it's doing a radiant heat load, you size the plate heat exchanger and the size of the circulator. So this becomes your thermal storage, your battery, so to speak. And then the plate heat exchanger just pulls out whatever rate of heat and whatever temperature you need out of that. This happens to be a chilled water tank that we're doing cooling out of, but the same concept applies there. And this is probably the more standard, more common indirect type, where the fluid from the boiler would go through the coil in there and come out and would heat the tank. Now, I've seen these pipe both ways. Some people say, well, wouldn't you want to put the hot water in at the bottom where the coldest water is? Yeah, you could do that, but what the intention here is I want to heat the top part of this tank as quickly as possible. So if I've got a call for domestic hot water, I'm heating the top of the tank first. It's like an electric water heater. You know how the top element always kicks on first, raises the temperature at the top of the tank, so you've got hot water, and then it kicks down to the bottom element to finish it off. So either way. All right, so that's what do you got for questions there, Kevin? Anything, or we can do a little video and we can come back for questions.
Well, I've got a really nice comment here from Mark. He said, I have 3 houses with hydronics. One has all radiant walls, one with walls, floors, and steel panel radiators, and one with radiant ceilings and radiant windows. And he prefers the radiant ceiling overall. I hadn't heard that before.
Yeah, I've been in one of Mark's. Yeah, thanks. I've been in one of Mark's house with the windows, and it's a pretty amazing thing. But you know what? There's pros and cons to everything. What I like about the radiant ceilings is you've got a lot of surface area up there to play with, so you can get you got a huge radiator basically what you have. So yeah,
really
and
interesting.
Floor coverings on it, obviously, on the ceiling, so you've got pretty much an encumbered radiator up there. So yeah, thanks for the.
Yeah, thanks, Mark, very much. I'll look for some more. Bob, go ahead with your video.
Yeah, I'll do a video. And again, this is just kind of a little tool tip thing. It's not really heat transfer related, but I thought maybe somebody could find this useful and use it. So I'll just play this. All right, here's a little tool tip for you. I work with copper pipe quite a bit, both for art projects and undoing and redoing different projects in my shop. So I took a block of wood here, just a 4x6, and I bored a 7/8 hole through it and a 5/8 hole through it. So what that allows me to do is just take and if I want to clamp some pipe in there, now I can work on it. I'm going to drill it or polish it or work on it. And then what I did on the other end here is this is a 3/4 hole here, and this is a 1-inch hole. And so what that allows me to do is put a fitting in here like this, and I can put this in the vise. Since I'm frugal or cheap, I use the fittings over and over again. Some of these fittings I've used probably a dozen times, and now if I want to get the solder out of there so I can use it again, I just take a 5/8 hole saw like this, cleaned it out, and there's a perfectly reusable fitting gun. Some of these I've had probably for years that I've just taken apart and used over and over again. So block of wood, couple hole saws, there you go. All right, let me close this out.
Bob, you're a genius.
I don't know about genius, but I'm just cheap. I hate to throw a copper fitting out, and sometimes I get so much solder globbed in them. You spend an hour with your pocket knife trying to get it cleaned
Yeah.
out. So I just came up with that idea. I saw the blocks. I got that online somewhere. That wasn't my idea, but I thought it was pretty clever.
Jared has a question here. When installing 2 indirect tanks for thermal storage, do you feel parallel or serial piping is best, assuming that both tanks are the same size?
Yeah, there's pros and cons to both of those. I mean, when we used to do the big custom homes back in Park City when I worked there, we would put water heaters in series, and basically what you would do is you could just run on one most of the time, and when they had a house full of people and they had ski guests or something in, they could turn up the one. The first tank was kind of like a preheat tank. It would just let whatever water came in, it would get to ambient room temperature in that tank. And then the second one would be the final feed. So that way it gave the ability to, double them up or have the other. I've seen people parallel pipe them too. It's if you do that, you've got to pipe them properly so that you can, webcam back on here, that you get the same amount of flow through both of them, which takes kind of like, what do we call that? Like a moose antler type of, a piping to make sure they get or balance valves to make sure they get the same amount of flow on them. I think he's meaning for the output side, and the as far as the boiler side, the same thing. You could you'd probably want to pipe them so they both get the same supply water temperature, but you could, we've done that with solar tanks where you've got the a double coil tank and you let the solar do the bottom of the tank, and then you let the upper coil connect to the boiler, that if the solar can't keep up or doesn't get it warm enough, you just kick onto the the upper coil. So yeah.
And here's a good one from Howard Hansen, referring back to your hot dog. Aqualung, is that what Ellen said?
There you go.
Aqualung, that's the name?
Max put that on.
Where do you bleed the air out of the dog?
Next one.
I don't. That's a good question. I just shove enough flow through it that it just kind of like a a Gianomi type of heat exchanger. You just kind of drive enough flow through that and blow the air right through it. So it had a pretty small diameter. I think it was 3/8 gas flex or ward flex. I don't remember what brand I used. So yeah, it blows out pretty quickly because there's no way to get a bleeder in there without coming out his ear or something, I guess.
Yeah. Does anybody want to raise their hand and ask a question? We have a few minutes here. I'll watch for that. That's about it for the questions, though, Bob.
Yeah, and I had a couple that were sent in. I think I answered them through the I printed those off that were pre-submitted questions. I don't know if you can see those on there, Kevin, but trying to think what the one was. It was a question from last week, actually, I think. Yeah, I guess I don't have it here. Yeah, well, I mean, then I guess we'll call it a wrap. We had a good turnout tonight. Thanks everybody for showing up, and that's how you can get a hold of me if you want to chat, or if you have questions on something, or if you have something you want to teach me. I'm certainly willing to learn. If you've got some clever tool tips or something like that you want to try out, let me know, and we can certainly do that. And like I say, next week we'll be back on the demo board. I don't know if you can see that.
You could show them your glove.
I was going to show you some kind of turbulent flow condition over on this. I don't know if you can see that at all. You can see how the flow is going on. Maybe not. My lighting's not so good in here. Sorry about that. But yeah, we're gonna have that demo going again for next week. When I put some food coloring, and the color helps it jump off a little bit better, and you can kind of see that turbulent flow going through there as I change the pump speed and that play around with the balancing valve. So.
Can you put that bare concrete output graph up again, just for a second? Jim wants to take another quick look at that if you still have it.
Yeah, and these are, I think it was way up at the top, wasn't it? These slides are available if somebody wants them. We'll, at the end, just let us know where you want them to send them. We'll probably turn it into a PDF so it's easier to. I think it was at this one. Not exactly a bare slab. It's got a little bit of hardwood on top of it.
Yeah, was that it, Jim? Did you want to raise your hand and ask a question about that? Here's a hand. Well, let me see if Jim's got his hand raised. He doesn't, but here's a hand raised. Gabor, is that how you pronounce your name? You're unmuted.
Hello.
Gabor Milicic? Sorry, I probably mispronounced your name.
Bob, I did find those pre-submitted questions.
Okay.
If you want to try to answer this, but one of the questions was, how do you size a heat exchanger for a snowmelt application?
Yeah, and I think that's one I covered. That's why I put that little graph in there. I'm using that. Every brand has a little simulator like that. Sometimes you have to agree to some terms or something to sign up or register to get it. But yeah, you can just go in there. If you need some information, you need to know what the load is on that. You need to know what kind of supply temperature your boiler is going to be able to supply to it. And then you just start plugging in some numbers. And it's usually they spit out a couple different choices, depending on what kind of delta T and stuff you want to run. They usually give you 2 or 3 different choices. But you can try the simulator. And most of the people, if you call them or send them an email, some of them have that live chat on the bottom of their website now. If you need help sizing that, they'll give you some tips, because sometimes they can optimize it for you and put you in a price range that works out too. So yeah, that's what I would suggest. I mean, you can do the longhand. The math is in fact, I think it's in the back of this Hydronics. There's a little formula for sizing plate heat exchangers like I showed you in that one slide, but I like clicking buttons instead of doing the math. I'm not a good math person.
Okay. And any tips, Bob, on yearly maintenance that needs to be done on heat emitters that you can share?
Yeah, that's the one I thought of. So yeah, that's a good question. I mean, it would depend, of course, on the type of heat emitter. Not much to do on a radiant slab other than sweep it once in a while. But if you have a fin tube, sometimes, especially if you live with pets, they can get dog hair and their dust and stuff, and can build up on them, and you don't get much output. You might have to get in there with a little vacuum cleaner with a brush on the end of it. The same thing with like a forced a convector, kind of like when you have to clean out underneath your refrigerator out now and then, because all the lint and dust gets plugged up on the coils on the underside of your refrigerator. So those would probably take more maintenance. Obviously, if you have a coil with a heat exchanger in it with a ducted type of system, filter maintenance would be important on that, so you get enough airflow across that coil, across that heat exchanger to get the performance that you need. So another reason why I like radiant slabs is pretty low maintenance. Just keep the water flowing through them and they work.
Hey Bob, would this slab output mathematic calculation work the same for radiant cooling, or is it different?
It would be a little bit different. In fact, it changes a little bit for radiant walls and radiant ceiling on this multiplier, because what happens on a radiant ceiling, even though you've got more surface area and you can usually run them a little low temperature, it does stratify a little bit up there. I mean, there is a little bit of air movement. So this number goes down, I think it's 1.7 on a radiant ceiling that you'd use for a multiplier. But we're going to have a radiant cooling webinar, a Coffee with Caleffi, at the end of the month. In fact, my son Max, who I guess is tuned in here, is going to be doing that. And I'm never done one, to be honest with you. I'm certainly not an expert in that area, but I know that's an interesting topic now, especially with all the new heat pump technology coming out, that we can heat and cool from one source, that people are going to start considering radiant cooling.
Yeah, thanks. So Greg, tune into our Coffee with Caleffi webinar on Thursday, the 21st at 12 o'clock Central Time, and that's when Max will be talking about radiant cooling.
Yeah. Thanks.
Nice.
All right. Got anything else, or? Let's see,
when will you be doing the hydro separator? Next Monday?
Yeah, next Monday. I think, let me look at next Monday. The what is today? The 4th is today the 4th?
Mm-hmm. The
May
11th?
the 4th be with you is today.
May the 4th.
Yep. So Steve, that will be on the 11th, next Monday night. Bob will talk about hydroseps.
Yeah, same bat time, same bat station. But yeah, that's going to be interesting. I got some really interesting things to show you about hydraulic separation. We kind of pioneered that, I'd like to think, Caleffi in the US, because we brought that product over from Europe, where it was developed for, specifically for high pressure drop boilers, is kind of where that started. So, and of course, got a little bit of a Gil Carlson spin on it too, because it basically is a primary secondary piping arrangement in the box. So yeah. All right. Oh, did you guys see my silverback? My wife said to show you that. I use that when I'm working on things here. They make these little gloves with magnets in it, so you can keep. I use those when I used to do a lot of overhead heat transfer plates, because all the screws, you keep dropping them, so you put your screws on there and you've got them right up by your hand. So that's my silverback. All right.
Well, I think that's it, Bob. And you'll remind everybody, these questions, we'll get back to you. That's all I have here, Bob.
All right.
And just
Thanks, Kevin.
importantly, if you want to donate to Meals on Wheels, there'll be a survey at the end of the webinar. Just plunk in your amount and Caleffi will match up to $500. So we just wanted to have a concerted effort in helping our elderly population. We know they've been hit hard by this crazy COVID thing. So, and be sure to tune in next week. More fun.
Well,
Hey
thanks.
guys, real quick, someone asked, what's the date again for Max's coffee with Caleffi?
Was it Max who asked?
No, someone asked.
Thursday,
No,
Thursday the 21st.
That wasn't funny,
Say that
Alan.
again?
Yeah, it's always we try and do them the last Thursday of the month, and that's noon Central Time too, so you know the time thing. But yeah, I think we should get you invites out for stuff like that if you're in our database, right, Mary? Don't you send them out to pretty much everybody?
Yep, it's coming out tomorrow for our general audience. So Thursday, May 21st, playing it cool with Radiant. So Max has got a wonderful presentation and lined up for our audience. So you got to join us for that one for sure.
Yeah, that'll be fun.
Yay.
During working hours too. Well, thanks, Mary, for that nice wrap up, and Kevin and John and Tim and the Mechanical Hub people for sponsoring this and making this available to everybody. It's been fun so far, so I hope everybody else is enjoying it, and we'll keep doing it. And everybody stay safe and healthy out there, and hope to see you in person again someday soon. So thanks, everybody.
Thanks, Bob.
Thank you.
All right. Good night.